holy crap, I'm on. We've got, I think we got like a minute until it's time for me to get started, so I'm just going to sit up here and talk about nothing of consequence until we get started. Is that okay with everyone? Cool? It's like, we just came here to see the fat American talk about nothing important. So, actually, thanks for spending your lunch hour here. It's much appreciated. So, quick show of hands. Who was here for the deep dives? Okay, and here, obviously, who's here for this? That should be everyone. Who was here for, I guess you would be both too, wouldn't you? So if you've been here for the deep dives, your brain is probably pretty full already, isn't it? Isn't it good that we got 2 more days of this? It's a fantastic, there's a ton of learning going on. So we still got, we're not at 105 exactly yet. And I actually like to start my talks, actually we're at 105 now. So what I like to do is I like to start my talk at 105 and 59 seconds, because that way I can still be on time, but there's always that person that walks in at the last minute, and then they just happened just now. And it's always awkward because I call it out by mistake. But we're going to go and get started. So welcome, everyone. I hope you're learning tons. My name is Guy Royse, and this is my humble little talk called Understanding Probabilistic Data Structures with 112,092 UFO Sightings. Full disclosure, this is a 60-minute talk that I'm going to cram into 45 minutes. So we will either go really fast or I'll skip a bit. But maybe a little bit of both. We'll see what happens. Or we'll just go over and screw the program, right? No one cares. So I'm Guy Royse. I'm a developer advocate at Redis. There's really only one thing that matters on this slide. I mean, I like to joke that there's 3 things that matter on this slide, because one of them matters to you, the audience, and one of them matters to me, the presenter, and one of them matters to my boss. So he would like you to know that Redis does lots of things. It's more than just a cache. Who here has used Redis before? Almost everyone. How many have used it for something, used it as a cache? Who has used it for something else? That's more than usual, but it's still, I can count you on one hand. So part of the point of this talk is to get you to think a little bit differently about Redis. We have things like probabilistic data structures. There's all kinds of capabilities that are underutilized. So that's part of my goal. But mostly this talk is not going to be a sales pitch on how awesome Redis is, even though it's a lunch session. It's mostly about the probabilistic data structures. I'm going to show you how these things work in detail, what they are, why you care, what you can use them for. I'm trying to give you another tool that you can put in your toolbox as a developer. And I will show you how you can use them in Redis, but that is a very small part of this presentation. The bulk of this is about the probabilistic data structures themselves. So the thing that matters on this slide to my boss is the Redis logo. The thing that matters to me is all the social media links there. I realize it's out of date now. I need to use the X. But it still has the little Twitter logo, so appreciate it if you give me a follow on Twitter. And the thing that matters to you is the GitHub URL. So that github.com/Guy Royse. I've got the slides that I'm presenting today. I've got my sample code. I've got some implementations of probabilistic data structures that you can go poke around with yourself. And I just want to humble brag that I've got guy.dev as a domain name. So, with that out of the way, 112,092. This is a surprisingly large number. This is the number of UFO sightings that I have in my data set. I say it's my data set, but it's really not my data set. It's the data set of the National UFO Research Center based in the United States. And from about 1950 to, I'd say, 2019, when this data was screen scraped, this is the number of sightings that were found in the United States. It's actually a lot. That's like, let's call it a 70-year period, maybe. That's more than 10,000 a year. Is that right? More than 1,000 a year. Math is hard. But it's a lot. And this data is from the National UFO Research Center. But there's a wonderful guy named Tim Renner who I always give credit for putting this data together. He screen scraped this site. He created a CSV file so that he could do fun and weird analysis of the UFO data. And what he used it for was he wanted to, he did some machine learning stuff. But he mostly just did some basic analysis, like he figured out where UFO sightings tend to happen. Spoiler alert, it's within 100 kilometers of US air bases. So that was one of his big findings. Another big finding is that the most common day of the year, he did a little histogram, and the most common day of the year for a UFO sighting in the United States of America, any guess? 4th of July, that's correct. I always picture in my mind, I always imagine this, like this father and son are sitting out there getting ready to watch the fireworks, and the son says, "Dad, is that a firework?" It's like, "No, son, that's a UFO." Incidentally, the second most common day is New Year's. So that's the second most common day for UFO sightings. So I guess they celebrate the same holidays as Americans do. Those pesky aliens. But he's got other data he's done this with. He's done it with Bigfoot sighting data, and he found where Bigfoot tends to be, where you can find Bigfoot. And he did some clustering algorithms and discovered that you can find Bigfoot in the woods. So important work. He's doing the Lord's work here. So Tim's a great guy. He's provided this data for free for everyone to use, and I've gotten a ton of mileage out of it, and I can't thank him enough. So the data itself is, in some ways, rather mundane. It's kind of what you'd expect. You've got it's a CSV file, and so it lends itself to, a basic hash table structure here. You've got your summary, which is sort of just a short description of the event. Here we have 3 saucer-shaped ships. Say that 3 times fast. High in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation. Definitely sounds like the Air Force. I mean a UFO. This happened in Salem, Oregon on September the 15th of 1950. And so you've got the city, the state, the date and time where these UFO sightings occurred. You've got the shape of the UFO sighting. This one was a disk. Shapes are interpreted kind of loosely by this data set. Valid shapes include light and object. So I guess those are shapes, but sometimes they're triangles and stuff like that too. So the duration is just more of a human-readable thing. It was a couple of hours or a few seconds or 15 minutes or whatever. There's a link to the New Forks website to that Bigfoot site or that UFO sighting. There's the full text of the account from the eyewitness. These are delightful to read. I go through occasionally, pick a random one and read them. And you've got the latitude and longitude of the city where the sighting was reported. So this is the data we're going to play with today as we explore what the heck is a probabilistic data structure. And I'm not going to answer that question yet because I want to answer a different question. I'm going to talk about a different question. But if you're wondering what a probabilistic data structure is, A, you're in the right spot, but B, you're not alone. So I did this survey when I was putting together this talk, a very unofficial Twitter survey. I had 119 people vote on it, so it's very scientific. But I asked everyone, and about 60%, 3 out of 5 had never even heard of them. About 20% had heard the term. Now, I suspect that the people that heard the term heard it in the question, and so I think they fall into the never heard of them category. Which means that 1 out of 5, 20%, either know what they are or have actually used them. So if you don't know what a probabilistic data structure is, you're in good company. This is true of most developers. And like I said at the beginning, part of the purpose of this talk is to show you what these things are and how they work and how you can use them so that you have another tool in your pocket, in your toolbox as a developer. But to understand what they are, I want to talk about their evil opposites, the reptilian to their grays, the deterministic data structure. You know what deterministic data structures are, but you've probably never called them these. These are the data structures that you use all the time, the lists and the sets and the arrays and the trees and the stacks and the queues and the tables and all those sorts of things. And they're called deterministic data structures because, well, they do what you tell them to. Like if I put data into a deterministic data structure, I will get it back out reliably, consistently. And if I add more data to it, it won't change the state of it in any way that means I can't get the old stuff out. So it's 100% predictable. And we use these all the time. If you are a programmer, you use deterministic data structures. I'm going to focus on how one of these works before I get into how probabilistic data structures work. And so if you've taken a computer science program at university, which is probably a lot of you, you probably took a data structures class. And this will be review from something that you haven't looked at or thought about in 20 years. So how do hash tables work? We've all used hash tables, right? We're probably mostly Java developers in here, right? I mean, this is DevOps. And so a hash table is a hash map behind the scenes in Java. If you are a Python developer or a can I say .NET in this room? Is that permitted? Yeah. If you do Python because you're a data scientist, or if you do .NET because you're sad, then you would call these dictionaries. And if you're extra sad like me and you're a JavaScript developer, you call these everything. They're all objects, and every object is a hash. So, but a hash table it's the key value store, right? We all know what a hash table is. We use these all the times. They're maps. You give it a key, you get the value out. You give it a key and a value, it sets the value in that key. And so, but how do these work internally? And why are they called hash tables? Well, they're called hash tables because they use hashing functions. A hashing function is, in simple terms, something that takes some data. Like right here, I've got some bytes that actually says Scully in ASCII or UTF-8, it's both. And you take a seed number, and given that seed and given the data, you will consistently get a numeric value out, a hash. And it's a one-way thing where I can turn the data into a hash, but cannot easily turn the hash back into data. And lots of times when you talk about hashing functions, people think of cryptographic hashes, like SHA-256, or the much maligned MD5. And these would work for a hash table, but they're not the ones you would choose. And you won't use them in your probabilistic data structures either, because those are geared for small changes to the data do not create small changes to the number. They have a very random distribution in the numbers they generate. Whereas for a probabilistic data structure or a hash table, the hash you would want to use would be more, you still want a good distribution, but it doesn't really matter if it's random. It just needs to be well distributed. And you'll see why in a moment. But it's mostly about performance. So something like a murmur hash is going to be very fast, whereas a cryptographic hash is going to be more secure, but it's slow. And we're more interested in speed than we are security. But this is what a hashing function does. It takes data. It could be a few bytes, or it could be a gigabyte, and hashes it down to a single numeric value, maybe like a 32-bit integer or a 64-bit integer or 256, whatever, an integer of a particular size. And we use these hashing functions in hashing tables to create the indexes to find out where things are stored there. So the way a hash table works is you take a key, say I want to store the city of Salem for our UFO sighting, into a hash table. So I take the key right here, I run it through my hashing function with my seed, and I get a number out. I get that hash out. And then I will modulus that with a number which is equal to the size of the hash table. So this hash table here on the right is an array of linked lists. I have made my array 10 characters, or 10 elements wide, or tall, I guess. And I've done that mostly because it fits on the screen in a font that you can read. But you modulus it with the size of that, and then you get a number from 0 to 9, and it gives you an index. And then in that index location, you put the value you want to store. You add it to that linked list. So city comes in, turns it into a number, turns it into an index in the array, and it adds it to the linked list at that location in the array. Make sense? Everyone's had this. This is a refresher, right? If we come in and add something else, let's say we're going to add the state of Oregon, goes through the same process, gets a different index, goes into the linked list. Occasionally, what will happen, eventually, inevitably, what will happen, is that you will have a collision. So when we go to add the shape of the UFO sighting, it turns out it has the same index. And this is why we use a linked list, because when we go to add it, we can say, well, there's something here already, and it's not us, so let's go ahead and add it to the list. So you get a linked list, an array of linked lists. When you go to read it, you just reverse the process and say, I want to look up the value city. You get the index again, you walk the list till you find city, and return it. So that's hash functions in 3 minutes, or hash tables in 3 minutes. How are we doing on time? Oh, terrible. So when we pick our data structures, like, say, a linked list versus, say, an array, we are usually often making a trade-off between how fast it is, what the time complexity is, versus how much space it uses, the space complexity. So if I have an array, it's space inefficient because I'm not necessarily going to fill that array all the way up. But it's very, very fast because I can go straight to the value. If I have a linked list, it's very space efficient. It takes up exactly the amount of space it needs, but accessing it can be slow because I have to walk the list to find the thing that I want. And so this is a trade-off that you make. So if you're in Java and you want to use a list, you can use an array list, or you can use a linked list. And these have these characteristics. So one's going to be faster, but one's going to be more compact. And so this is a trade-off we make when we select our data structures. But it's a little bit of a false dichotomy because it's not always the trade-off we're making, right? Sometimes the trade-off is capabilities. Like, do I want a linked list or a hash table? A hash map, right? Why do I pick a hash map versus a linked list? That's because my data is structured that way. It's key value pairs. And so there's other reasons other than just time and space that we use to select the data structures we select. We also will look at its capabilities. And one of the trade-offs that you can make that you might not realize is you can choose accuracy. You can take a data structure that lies to you sometimes, and where things that you add to it don't necessarily stay there, or it'll tell you that things are in there that aren't in there. And it has limited numbers of operations. And this is, in essence, what a probabilistic data structure is. It's a data structure that sacrifices accuracy to get orders of magnitude improvements in speed and space. So, as a developer, you usually get a little bit of a visceral reaction to this. You're like, no, it must always be perfectly accurate. Right? You're probably feeling it right now. It's like, this sounds like a terrible idea. Why the hell would I ever want these things? Well, it's about scale. And sometimes you don't care how accurate the number is. Let's say you're a popular video sharing platform called MeTube. On MeTube, you want to see how many unique viewers have watched a video. Now, when you're at like 10 or 20, you care how accurate that number is. But when you're at 1 million, does it really matter whether it was 1,013,000 or 999,997? Or is that close enough for your purposes? That's the problem that probabilistic data structures help you solve. And if you think about it, you've been using them for a long time. This right here is a JPEG of the Devil's Tower in Wyoming. It's in southeastern Wyoming in the Badlands. And if you've seen Close Encounters of the Third Kind, which most of you probably haven't because you don't remember the 70s, this was featured in that movie. That's where the aliens came and met everyone. And Richard Dreyfuss sculpted it out of mashed potatoes. That actually happened in the movie. You should watch it if you haven't seen it. It's great. At least 8-year-old me thought it was great. It's got to be a good movie. It came out the same year as Star Wars. So, anyhow, this picture of the Devil's Tower here is actually a JPEG. And you see that blue pixel right there? Yeah, you see it? It's actually the wrong color of blue. Do you care? No, you don't. It's a little bit lossy. This isn't perfectly accurate, but it's good enough. And that's the problem that probabilistic data structures solve. You can think of probabilistic data structures, at least the ones I'm going to talk about today, as sets, like set theory sets, the whole Venn diagram thing, right? With peculiar properties. So if you've got a set, you can add things to it. You can remove things, you can get things, you can do unions and intersections and get the cardinality and those sorts of things. A probabilistic data structure is a set that has a subset of those attributes. So like you might have one where they all can let you add things, because otherwise they'd be useless. But you might not be able to remove things, or you might be only able to ask, is this thing in the set? Well, you may or may not be able to do unions and intersections. But they're probabilistic data structures that are limited they act as sets that have a limited group of capabilities. You can have ones that are optimized around testing for membership. They say, is this thing in the set or not? You can add things to the set and then say, is it in the set or not? We're going to talk about Bloom filters. This is what it does. And so this is, the use case I always like to think of for membership is a username. Let's say you're Facebook, and you need to see if a username's taken or not. So what's not going to work? Select star from users where username equals the name I'd like to pick. That is not going to work for Facebook. What you can do is shove all your users into a set that's probabilistic and say, is this name taken or not? And if it says yes and it's lying to you, then no one's getting that username. But that's okay. They can pick a different one. Right? So that's the sort of problems you can solve with membership. Cardinality is about counting things. So that unique user is on a MeTube video. You could add all the usernames to that set and then say, how many things are in the set? And it will give you a number that's accurate enough. You can do frequency. So this is sort of stretching the idea of what a set is, where if I've added the same thing to a set multiple times, I could maintain a counter to go alongside of it, and I could then get an idea of how many of these things are in the set. And those counts would be inaccurate, but accurate enough. You could do ranking. This is kind of like frequency, but instead of worrying about the count being accurate, it could be wildly inaccurate as long as the relative order is the same. So we could go and say, well, hey, set, give me the top 5 things. We're going to look at top K, which does this. And you can do similarity on these sets, too, where you can say, how similar is this set to another set? So this is some of the stuff we can do with probabilistic data structures. We've got a lot of choices to choose from here. Up on this list here, we've got, you notice they got the little red dagger there and the little red double dagger. So what the red dagger means is that it is, or any of the little annotated ones there, means that it's part of Redis, and so you can use that probabilistic data structure in Redis. Hyperlog log is the only one with the double dagger. That is in the open source core Redis, whereas the one with the little single cross-like thing is part of Redis stack. And the ones that are highlighted in blue up there, those are the ones that we're going to talk about today if I don't run out of time. So, and I mentioned Redis stack, and so this is the one plug that we're really going to get for Redis here is Redis stack is regular old Redis with extensions to add new data types like JSON, search, a time series data type, and Bloom filters, which is, Bloom has the probabilistic data structures in it. And you can get it at redis.com/tryfree. So go check that out if you want to play with these things. And we're going to talk about Bloom filters first. I've got, looks like I've got 23 minutes still. I think we can get through all this. So a Bloom filter is a set that you can add things to. You can only add to it, you cannot remove. And it will respond with either no, and it'll let you test for membership. Is this thing in the set, yes or no? It will respond definitively with a no, or it can respond with a probably. So you can get false positives, but you can't get false negatives. They're really interesting because they're fixed size, so when you create them, they are of a size, and they don't get any bigger. And every operation on them is O of 1, no matter how many things you add into it. However, because they are of a fixed size, if you fill them up, if you keep adding to them beyond what you build it for, it will get really happy and always say probably. It'll be super optimistic. Is that in the list? Yes! Yes, it is. It's like it's an American. So inside of a Bloom filter, you've got some hash functions with seeds. This is why I talked about the hash table stuff first. And so we're going to use those hash functions and probably take the values that we're going to put in the Bloom filter and hash them. And you've got up here a bit array of a fixed width. I've got 10 bits here because, again, it fits conveniently on this screen. And the way they work is you add a value to them. And so I'm going to add various UFO sightings. This one first here is called Megatron in the Bushes. This is probably one of my favorites. It's this great story, if you go out and read it, about these two guys who were driving down the road I think in Arizona or New Mexico. Probably New Mexico, because that's where Area 51's at. And they had to pull over to take care of a necessary but important bodily function. And so they pull over, they find a bush, they go back behind the bush, and they hear Megatron from the Transformers. They hear him transforming. Right? You know that sound that they make, that. Yeah. It's my imitation of Megatron. They hear that behind the bushes, and so they freak out. And they get in their car, and they take off driving down the freeway, and then these glowing lights come from behind the mountains and chase them down the highway for like 100 kilometers. And I'm sure they were not high. Certainly no drugs involved there. Probably no alcohol either. So, but anyhow, it's a great story. It's really funny. We want to know if we've seen this before, so we're going to add it to the Bloom filter, and then we can say, have we seen this before? So what we do is we take that string, we feed it through our hashing functions, we get a hash, we get a unique number, and we do a modulus of those with the width of our bit array. These give us indices, and then we go to those indices and we flip the bits. All zeros become ones, and all ones stay ones. We just set them all to high. And then when we go to read from this, we can do the same process and say, are all of these a 1? If they are, it's probably in the Bloom filter. If any of them is a 0, it's definitely not, because this value hasn't come in to set the ones. Right? One of them is a 0, it's definitely not in the Bloom filter. So we added Megatron in the bushes, read it. Here we're going to add another UFO sighting. I seen a UFO when I was about 13 years old. Yes, the Yelly case is part of the actual data file, so I preserved that for all the important reasons, and the bad grammar. And so in this one, we do the same process, and we get some indices, and 2 of them are unique, but one of them overlaps with the previous thing that we added. And this is fine. This is why we have multiple hashing functions. We had a single hashing function. This collision would then result in more false positives. This reduces our false positives. But it does mean our bit array needs to be wider because we need to store more things in it. So if we read I seen a UFO, we get all 1s. If we read Megatron in the bushes, we get all 1s. They're both probably in the Bloom filter. But here's where it gets interesting. We're going to add a third value to the Bloom filter. Investigators from the Bigfoot Field Researchers Organization observed a glowing green-blue sphere. When we run this through the hashing functions, they all collide. 0, 1, and 6 already have 1s in them. And so if we add this, it doesn't change the state of the Bloom filter. If we then go and read it and say, is this in the Bloom filter, and we added it, then it's going to say, yes, it's probably in there. If we ask, is it in there, and we haven't added it to the Bloom filter, it's also going to say, yes, it's probably in there. This is what makes it probabilistic. That sort of indeterminate, it's not indeterministic, that's not quite the right word, but if I had added it, it would be correct. If I hadn't added it, it would be wrong, but the state's the same. And if I had added these in different orders, I would have got different results. And so this is what makes them probabilistic. One interesting thing here, I mentioned how Bloom filters get full. Does anyone see how they can get full looking at this? Right? If I put enough things in there, eventually all those zeros are going to be 1. And no matter what you put in it, it's always going to find 1s, and it's going to say, yep, probably in there. So, Bloom filters. There's some math to figure out how to compute this. I'm going to skip it because I don't really have time, and who cares? There's an online calculator you can use instead. Or you just ask ChatGPT, it'll know. If you want to use Bloom filters in Redis, you could use the bf reserve command. You give it a key name, you give it an acceptable error rate, it will do all the math behind the scenes for you. And you say, I want it to only lie to me 0.5% of the time. And I want to put 100 things in it, and it will build one of an appropriate size. And then to use it, you can use the bf add command. And so you say bf add, and then you give it a key name, and you give it the thing you want to add. And there's the mad command, which is the multiple add command. We like to pronounce our Redis commands, so the mad, just funny. Actually, there's the set add command in Redis. It's just the sad command. It's the loneliest of all the commands. And although my favorite is probably the H increby, which increments a numeric value in a hash, and we call it Hinkerby. So lots of fun names here. And so you can add, and then you can call exists. Does this exist in there? And then we've got a multiple version of that, which is mexists. So that's how you can use this in Redis. You can code one of these up yourself. I've got some sample code in JavaScript that you can look at. And I actually used an array of Booleans, which is super inefficient, but it demonstrates how it works. So that's Bloom filters. Let's talk about MinHash next. We might have to skip top K looking at the clock here, but we'll see. So MinHash, excuse me, what it's good for is it lets you see how similar documents are. So you can take documents and turn them into sets, and then compare those sets and see how similar they are. MinHash was created by Alta Vista. Who remembers Alta Vista? I think it was Alta Vista, they were bragging that they had 300 websites indexed on their webpage back in the 90s. Wow, how far we've come. So what MinHash does is they would use it to say, is this close enough, similar enough to a page we've already indexed to not return both of them because they're duplicates? Or is it worthy of reindexing? And so you can say, has this document changed enough to be worth a reindexing? You can also use MinHash to say, let's say you all wrote term papers, and the professor wants to see who's cheating. They can find which term papers are most similar, and then look at them more closely. And to compare sets, you need to have a means to do that. The means that is most commonly used is a thing called Jacquard similarity. Jacquard similarity takes two sets, and in simple terms, it's the cardinality of the intersection divided by the cardinality of the union. So the idea here is that you've got the union of this set. So here we got a set of, I'm pointing to my screen like you can see it. We have Scalder and Molly, face swapped from the X-Files, and they've got the states in the United States in which they've seen UFO sightings. And so Scalder has seen them in California, Nevada, Oregon, Wyoming, New Mexico, and Ohio, which is where I'm from. Molly has seen them in Florida, Kansas, South Carolina, West Virginia, New Mexico, and Ohio. So the intersection there is New Mexico and Ohio, which would be Area 51 and Hangar 18. So this sounds legit. And so the cardinality of that is 2, and then the cardinality of the union is 10. And so we do the division, and we say, oh, the similarity of these documents, these sets, is 20%. So they're 20% similar. A very easy calculation. Well, we could do this with documents and see how similar documents are, but the problem is how do you turn a document into a set? Because if you just put all the words in a document into a set, A, there's going to be a lot of duplications, but B, we're all using the same words. All you're going to establish is that both documents were written in English. That's useful, but that's a different use. That's a different utility. So what you do is you turn these documents into shingled sets. And what a shingled set does is it's a set of trigrams, three-word groupings that are overlapped. So to build our shingled set of this little snippet from the Megatron in the Bushes Bigfoot or UFO sighting, we take we notice 2. It's our first trigram, so we put it in the list. And then notice to our, because it overlaps, and to our left, until we fill up the entire set with all these trigrams. So we notice to our left, further off into the mountains, a bright glow. And so you can take these shingle documents and do a Jacquard similarity, and that's meaningful. It'll actually give you a similarity between those two documents, which is great. But it's not very efficient. If you think about everyone in this room, let's say you wrote a term paper and I wanted to see who was cheating from whom, how many connections are there? I got to compare everyone to everyone. It grows very quickly. And we're comparing strings here. Not efficient. So what MinHash does is turns these sets of strings, these sets of trigrams, these sets of shingles, into numbers. And it does it by using a hash. And so we'll have a collection of hashing functions with their seeds, and we will run the set of trigrams through that hashing function and get a bunch of hash values. And then from that hash value, we'll take the minimum value, the min hash. And we'll do that for several hashing functions, and we'll get a set that acts like a signature on these documents. And we can do the same thing for Scalder and Molly. You get different numbers. And then we can do the Jacquard similarity on those numbers instead of on the strings. And that's much more performant. And you can save these off and use them later. You'll note here that my calculation here is not as accurate, or it's more precisely, it's not as precise. And that's because I only use 3 hashing functions. I could use more, and you would get a more precise number. And it's still probabilistic, and so it's not going to be as accurate as actually using the string values, but it's a trade-off of accuracy versus performance. So that is MinHash. We've got 11 minutes. We're going to do top K next. This is the densest of them all, so, well, hold on to your butt. So top K is a thing that counts frequency. It'll give you like the top 10 most clickbaity articles, you know, in something or other. And so you can add things to it, and then it will give you the top things, the top most commonly added things. It's counting behind the scenes. Internally, it's got 2 pieces to it. It's got a min heap, which we're not going to talk about, other than to say that it's there, and a heavy keeper. And the heavy keeper is where the interesting stuff happens. The heavy keeper counts things, and it will keep the things that have big numbers, but the things that have small numbers, small counts, will be eroded away. Or things that haven't gotten anything in a while will be eroded away. And so it's actually really good for like trending topics or network traffic analysis. Like you could put IP addresses of whoever's hitting your server into one of these and then get like a top 5 list or a top 10 list of who's hitting me the most, and then figure out the IPs of things that might be like DDoS attacks. Or you could put trending topics into here and, you know, put your hashtags in there, and hashtags will naturally fall off as they stop getting used, and other ones will replace them. So it's a really interesting data structure. It's a little detailed. Heavy Keeper has several hashing functions again, and for each hashing function we have an array. And this array right here is however wide you want to make it, and each element of that array has a spot for a hash value and a spot for a count. And the way it works is if they're brand new, of course all these are null or empty. And the way it works is that as we add things, add values, we're going to add UFO shapes to our Heavy Keeper. We do a familiar process here. We're going to add the word object to the Heavy Keeper. It's going to be hashed. That hash is going to be modulus. We're going to get an index, and we're going to look at that index, and we're going to make a decision and say, so like on the first row here, we get a 2. We say, is there a value in the hash field? If there isn't, if it's null, then we're going to claim it. And so all of these are going to do this. So we're going to do this for each row, and our hash value is going to get shoved here, and we're going to take the count from 0 to 1. So we're going to increment it. So we've added object. If we add object again, we will do a similar process. We'll hash the value of object. We'll look at that index. We'll say, is this hash value right here, that 5062, is that match what I just computed? If it does, that one's mine. And so I'm going to increment the count. And then if we want to query the count, we can then go in and do that same, hash the string, get the index, look at the hash column. Is it ours again? Yes. Okay, there's the count. We do that for each row, and we take the largest number. And so we've added object twice. We query it. We get object out with a number of 2. So let's add a different value. We've got object, which is one UFO shape. Let's add light, which is the other one. So for light, we go through the same process, and in the first row, we get an index of 1. In the second row, we get an index of 2. But in the third row, we get an index, and we look at it, and it's like, oh, something's there. And we calculated 1352, but we got 1442 in there. So that one's not mine, but I want to put my stuff there. So what do we do? Well, this is where Heavy Keeper gets kind of interesting. What we're going to do is we're going to calculate a chance that 2 will be decremented by 1 to become a 1. And if it decrements enough and it becomes a 0, then we'll replace the hash value with a null, and someone else can claim it. And so this is how things get eroded in it. And the chance of the erosion is determined by this formula. The probability is equal to a magic number that is a value of greater than 1, but close to 1. So we got like 1.05. And you take that to the power of negative the count that's in there. So we've got 2 items, so it would be 1.05 to the power of negative 2. So that leaves us a fairly big number, right? We get 90.7% chance that it's going to be decayed. So we'll generate a random number, and we will then decay it if a random number says we should. However, if there's a lot of stuff in there, let's say the count was 10,000, well, that's going to be that's going to generate a small number, and so the probability of a decay is low. And so what this means is that as things get heavy, they get harder to dislodge. So it's a heavy keeper. That's why it's called a heavy keeper. Whereas things that never really get big, they come into existence, they're removed, they come into existence, they're removed. Whereas the heavy stuff will stick around. But if nothing gets added to the heavy stuff for a while, they will slowly get eroded away, and they'll fall off the list. And so this is why it's good for things like trending topics. So we're going to say that the erosion happens, and light in position down here in row 3 does indeed decrement that, so now it's a 1. So now when we go to read, if we look up the word light, we got 2 rows where we get a match, and 1 row where we don't. We take the biggest number out of the ones that we got. We got 2 ones, so it's 1. For an object, we find 3 matches. We get a 2, and a 1. The 2 is the largest, so we return 2. And so this is how the heavy keeper works. And just scale it up and keep iterating it, and it does lots of stuff. So, and every time we add something to the heavy keeper, we get that count back, and we will update the min heap, which has however many items we want to keep track of. So if we're keeping track of 5 items, like we're doing the top 5, then this has 5 items. And we will add that to there, reshuffle it, combine it, and this will give us a quick access to the most common items, or top 5 items. So that was real quick, and I realized that was real dense. I'm not going to talk about how to use top K. I'm going to skip right to my demo, because I think I can do it in 3.5 minutes. So the commands aren't particularly clever. They just do all the things I just said it does. And they're very well documented. So I figure everyone probably wants to see the demo anyhow, right? Like, is this real or is this just a bunch of bullshit? Let's show me a demo, guy. So there's my demo. Isn't it great? Yeah. Yay! So, okay, so I have written, I've got the CSV file here. Yeah, that font's big enough. That screen is enormous. So this is kind of old code, but basically what it does is it reads that CSV file, runs it through Natural Language Toolkit to remove things like the, and or, and that kind of stuff, because those would not be interesting top 10 words found in UFO sightings. And then adds them to the probabilistic data structures. That's all this code does. And I got a little app which gives me a little web interface on top of it running Flask. So I'm going to go ahead and kick off let's go to the build first. And go up here. And then that's going to read that CSV file through. And now it's going to start adding things. In fact, let's go ahead and do that. So, and then I'm going to run this guy here, app.py, and this is just going to, that's totally not how that's supposed to work. There we go. This is going to just put up a little web server so we can go look at it. I'm going to go into Redis Insight here really quick, which is a GUI for working with Redis. You can see that I've got a UFO shapes and UFO words structures here of type top K. If I go down to the CLI, I can do things like top K.list UFO words, and it gives us my top 10 words, and as I run that, I can run it multiple times. So we're updating these data structures as this is in real time here, but the GUI, honestly, this looks nicer. So let's go ahead and do this. And you can see that it's just polling it every second to get updated values. You see the most popular words are light, lights, sky, object. Popular shapes are light, circle, triangle, others a shape, apparently. So that's my little demo. This is all out on GitHub, so you're totally welcome to go out there and exploit it and update it and send me pull requests and tell me how much it sucks or how awesome it is. I'm good with all of it. So yeah, let me go ahead and get my slides back up here because I've got just a moment left. So it's a real thing. It does real stuff, right? So go check it out. Here's a whole bunch of links to stuff I looked at. This is out on the GitHub repo, so you'll be able to find it there. I work for Redis. We've got a Discord server. If you've got questions, go to discord.gg/Redis. We have free classes at universityredis.com. And if you want to get Redis Stack, go to redis.com/tryfree, or just Google Redis Stack, you'll find it. And we're in the booth. We can answer your questions there, too. Here's the thing that matters. We have a little slide here. You can QR code this. And that QR code is reliable. It will never give you up, nor will it let you down. And that's my talk. Thanks a lot.